A combination of what? What? CH4 is methane, so it's a combination of carbon and hydrogen. It took energy to combine those. It's not available in absolute form. It's not a specific individual species, so that's a very good point. Bring up a very good point. For reactants, it depends on what I have to deal with. If I have an absolute hydrogen, yeah, the problem I did earlier, that's the easy one, because I'm using hydrogen as an absolute, and I'm using oxygen as an absolute. But in reality, for propulsion systems, we're not going to be using those. We're going to be using a hydrocarbon of some sort, which is CH something. Now, air, in a sense, that's separated for me, because I have nitrogen and I have oxygen. But yes, for fuel specifically, you might have to account for that. But good point. Well, you had another question, right? You had another question.
Those two.
Okay. Any further questions?
Yeah, what are these things on the bottom?
What are these things?
The KR bar? Oh, okay, sorry, no, they're, sorry.
Oh, sorry, yeah, kilojoules per kilomole over A. Wow. Let me just rewrite it on a new page. Like the end of the page. Delta heat of reaction is equal to Q net over Na kilojoules over kilomoles of A, whatever A is as a fuel here, and heat of reaction is equal to the heat of reaction in terms of number of moles, or kilomoles, divided by the molecular weight of A, which will give me kilojoules over kilogram of whatever that species A that I'm using. And if it ends up, and we talked about this earlier, if Q net ends up being greater than 0, what is the process? Endothermic or exothermic? If Q net is greater than 0, endothermic. Now, we're not going to be dealing with endothermic in this course most of the time. We're going to be dealing with exothermic, because we are actually reacting that mixture to produce heat, and from the heat we can actually get work, and that's how we get our propulsion system plus. So, heat of reaction, or we could call it, so here's the thing, so heat of combustion. So to confuse even more, is delta HC. That's heat of combustion. Now what is delta heat of combustion equal to? What? So the reason why we have heat of combustion, because from the combustion standpoint, heat is a positive thing for us, because that's where we're actually getting work, or thermal expansion. So we can't take heat of reaction as a negative, because based on this exothermic, what does that say about heat of reaction? What is heat of reaction going to equal to here for exothermic? Positive or negative? Negative. Negative, right? So in reality, delta heat of reaction is going to come out negative. Now, from a combustion standpoint, it's a positive, really. So what is delta HC equal to? Minus delta heat of reaction. And that's going to be somewhere around 50,000 kilojoules per kilograms of your fuel.
So
That's why combustion becomes a very dominating energy source, because you get a significant amount of energy by doing this reaction. Okay? So should we do an example problem to tie in all this? Yes. All right. Yeah, the equation part of this is not fun, but once you start using it, you become very proficient at it. This is like, give yourself a few weeks from now, and you'll find yourself that this is the easy part. All right, example. Let's assume I have methane and air.
Feel free to find out and help you out. Who works at
At
automation?
400.
Miami, but he was. There's a way. You know the trade.
You have phi equals to 0.8. You know what phi is? What is phi? Equivalence ratio. Where did we see equivalence ratio before? Is it air to fuel ratio? Fuel to air ratio, is it only fuel to air ratio? Yeah. So what does 0.8 mean? 80% of what? Most of you know from last lecture. So P is equal to fuel of air, fuel relative to air, relative to fuel of air of storage. So that means, am I burning ideal here? No. If it's 1, then it's stoichiometric. But since it's 0.8, what does that mean? Am I rich or lean? Lean. Why? Because I'm putting less fuel relative to air. So in this case, it's actually lean. Lean fuel. We're going to compute it in a second, but so find, confuse even more, the lower heating value. You remember lower heating value, right? You have to do it at some point. So what is the lower heating value for us here?
I'll come out and say I've never seen that before.
You never seen it before?
Yeah.
Well, that's a good one.
None of us.
Lower heating value? It's in gas turbines, doesn't it? Okay. But thermodynamics. High heating value, low heating value?
We just really overestimated
All right, well, you're already familiar with it. So lower heating value versus higher heating value. The difference between them is the formation of water. So remember this problem. Let me just interrupt that thought process for a second. Right here. Hydrogen and oxygen reaction, right? I got H2O. I could get H2O in 2 forms. I could get it in liquid form, or I can get it in gaseous form. So when I say a higher heating value, that means it's this one, the liquid one. And a lower heating value is the gaseous one. That's the whole, in terms of enthalpy of formation or reaction. I could get enthalpy all the way till water is saturated and it's now liquid, or I could get it in a form that it's in gaseous form. Now for propulsion system, do you really want to get it into this higher heating value or lower heating value? Why lower heating value? So that's good. Lower heating value, but why? Yeah, you don't want water coming out of your exhaust, although it does happen in your exhaust, but you don't want water. You're dealing with gas. You always want to deal with the working fluid, as meaning the heating fluid, so you always work with the lower heating value. For us, that's heat of combustion. Okay? Make sense? Question?
It's slightly off topic, but if you had water in the backside of your gas if you're trying to inject it to the is cavitation going to be an issue?
Well, when you say water,
Well, not like liquid, yeah, and it's,
well, it's not going to be a lot.
okay.
It can't be a lot. I mean, what you're going to end up is you're going to be condensing that water down, and you're going to be getting a layer that's moving along the surfaces. But in reality, in the end, it's how much of your gas that you're actually passing through. So in a gas turbine engine, you're using air. Air is composed of nitrogen and oxygen. You're burning the oxygen, but the majority, the percentage, is almost 80% nitrogen. So that nitrogen is not going to condense down. So that's going to pass through. So if anything, now if I have a water layer right here that's saturated on the surface and I have gas passing over it, that's going to do shear and it's going to affect my flow anyway. So I don't want to condense it down to a liquid type form. So that's why we wanted the lower heating value. Questions?
Do they use wet compression though?
Sorry?
Do they use wet compression?
Wet compression? How?
Gas turbines, they blow mist of water into it.
Yes, but that's, again, mist of water is atomized. There's difference between that and actually having a condensed layer. If you look at your exhaust tip in your car early in the morning, you'll see that there's a layer of water that actually forms. That means you're not running at a full efficient engine condition right now. And once it actually warms up, you don't see that dripping of water that does happen from your exhaust car afterwards. Because now you're actually leveraging all the heat value that's coming out of your engine. Make sense? Okay, so back to this. We want to find heat of combustion primarily, or lower heating value, but primarily heat of combustion, or minus heat of reaction. Or minus heat of formation. We're very familiar with all these processes now. So